all our soft copy are available. Hello?
Yes,
Shall
sir.
I
Please proceed, sir. Yes, sir.
proceed? Yes. So I have given all these things to Mukesh. Anybody interested, they can take these books and they can directly contact me. I will share whatever I know with you guys. So I am going to give a just overall introduction, where it works, how it works, and result. In between, there is no point of discussion because everything is available in the books. You have to take care from the books and do the coding. So with this, I am going to start. What is this? 1 minute here. Huh. This is a filter. We use the word filter, but actually it is a work in the time domain. In the filter means basically it has been what I mean to say. People have this particularly filters have come out in sometime in 1930s to 40s during the Second World War. People started from the time domain to frequency domain. You must be knowing, and people do all the designs and all these things in the frequency domain because going from the time domain to frequency domain those days you have to use the Fourier transform. Subsequently, fast Fourier transform came in 1960s. So it was very easy in lieu of time doing the work in the time domain, because if you want to do the time domain work, if the equations are non-linear, in that case it is very difficult to solve because there was no computer those days. So the people used basically Laplace transform. Anything which is non-linear, they made it to be linear in the certain zone. Then after that they applied the Laplace transform. Then after that Fourier transform, you can go to the Fourier domain. I mean to say in the frequency domain, you do all the calculations in the frequency domain and do whatever you do. You try to stop after some frequencies. Then you come back to the time domain, so signal will be noise free. And exactly same concept was there in the control. Even today also control, they use the work in the frequency domain. Okay, so during the frequency domain, when you do that finite impulse response, infinite impulse response, then fast Fourier transform with different windows. So that's the way they use to filter the noise, and so that people can be using will be using particularly for their signal processing of the radar. So this importance of this technology got evolved in MIT Lincoln laboratory, and people started working area in this area, particularly in the frequency domain. And then after that, apart from the area came in the controls also. Control, you know, that Bode, Nyquist, they have done the breakthrough work. And even today also, people who are working in the frequency domain, in control at least, no way they can replace because of this gain margin, phase margin concept. So frequency domain, though had become classical, even today also in any application they are used. So I am going to talk about the time domain. So in the frequency domain, you know that notch filter is there, low pass filter, high pass filter, band pass filter. They are all worked at the frequency domain, and students are all learning in their signal processing course. Then time domain activity came much little bit later, because 30s to 40s, this when the Second World War, actually Second World War is the time when all these applications were implemented and people invented all this. Everywhere there is some devastation, at the same time there will be something good also. You think about your covid, there are so many problems, but we all got used to this media by using this internet and all these things, no? So that today distance is not a criteria. From here I am talking to you, Trichy, without any problem. So everywhere the technology improves during the any devastating devastating, whenever some devastation happens. So Second World War is the first point for signal processing as well as control, and even today they are working. So other domain of the signal processing comes under time domain. That comes under something called estimation theory. In the next slide I am going to talk about it. You know that estimation theory is what? Basically we all know the least square techniques. It is basically nothing but the fundamental is the least square, and any noisy signal is there, and if you apply some model, you see that from the noisy signal, actually when you use the filter, that means least square sense, you will be in a position to remove the noise. It is basically offline batch processing or weighted least square. Weighted least square means different instruments are there. Some of them have to be given more weightage and less weightage. Not it is one more level of least square. And this thing also was invented for online processing. That means recursive least square. And in some sense, Kalman filtering is a so-called recursive least square. And you know that in our control and signal process, there is something called state variables and measurements. Measurements is basically whatever the instrument measures, and states what represent the different variables, and your measurement is basically function of the states. So Weighted least square they use for flight data analysis and in the missiles. And online processing is the least square technique, and this is Kalman filtering. Example, from noisy position information, I have to get the smooth position, velocity, and acceleration. Just you have a look. This is a noisy signal I have generated, and from there you can always get derivative. Noise is signal when you calculate the derivative. This become, because as an example, y is equal to 5x of 7. You use a noise of 0 and 1 with 0 mean and 1 sigma. So y dot is basically what should be 5. But in the presence of noise, you see it is becoming minus 300 to 300. So, and in a physical problem, you cannot avoid differentiation. Why? From the position you differentiate, go to velocity, and from velocity you differentiate, so go to acceleration. So you have to do it because these are kinematics, and any particular missile case, like when it is going to hit the target, some guidance law that needs only position and velocity. And integration is your opposite process. Integration, if you have, then with the integration you keep on integrating, this noise will not be there. But once you do the integration, the initial condition of the integration is very difficult to know, so that itself creates a bias. So both the way you are having problem. Today I can tell you one thing: if the signal does not have any noise, control guidance engineers or control people or guidance, particularly signal processing people, they were jobless. They would have been jobless, and this technique would have never come. So differentiation in presence and noise very terrible. And noisy position, from there, how to get the velocity? This is called estimation problem. So that means the signal is there with the noise. From there, you calculate the derivative or second derivative. And derivative information, you don't need anything in the world more than acceleration. So that if we can do, so that is done by using so-called Kalman filtering with a recursive least square. So I think I have given the particular importance of Kalman filtering and where it is used. Okay, so this estimation theory I am going to talk now. I am going to give a historical purview so that everybody appreciates. And I have given the, I have already given the slide to Mukesh. You can go through the end, and from there you can go through in internet, and you will be in a position to get all the information about the people who have contributed. So historical evolution of the estimation theory, and the people, and if you know already, fine, but you see that how much the people have contributed. Huh. It is basically a branch of statistics. After all the this applied mathematics or what you call engineering is nothing but applied mathematics. So it needs statistics. One of the important area of mathematics is basically statistics, and deals with state and parameters and measurement. And I'll, after some time, I'll define what is the meaning of state and parameter using one example. And measurement, what your sensor measures. Like we're having so many sensors. Like as an example, I have not given here. You must be knowing that the instrumentation students, they will be knowing, particularly accelerometer, gyro, GPS, radar. They are all basically measurements. Actuator, they are all the hardware devices which measure something and give an output. Given an input, you will measure something and get an output. So estimator tries to attempt to estimate state and parameters from the measurements. Okay, state means position, velocity, acceleration. Parameter means in a flying vehicle there is something called aerodynamic coefficients, and one more thing called sensor bias. Sensor, when you will be using initial time, there will be some bias, and that bias will be remaining, and you just no way you can remove the bias. As an example, it comes in INS GPS integration. I will tell you one by one. And measurements can be what? Seeker can be a measurement. What gives the relative speed, relative position between pursuer and evaded. That means missile and target. Radar is one by which it will tracking the target. And after tracking the target, it will give you range, azimuth, and elevation, three important parameters. From there, you have to get the position and velocity. Then accelerometer measures the acceleration. Gyro measures the body rates. In a physically sense body, there will be pitch, roll, and yaw. And gyro are basically one sort of measurement unit. They are all kept in inertial navigation system, which does the navigation of the system, missile. EOTS, electro-optical tracking system. These are all the things like radar. By this, you will be in a position to track the target. As I told you, when you track, there will be invariably some sort of measurement noise. And measurement noise, if you have to remove that noise. And you have to, they are all available in terms of position. That means range, azimuth, elevation. From there, you have to differentiate, get the velocity. Second slide, I have shown you that with the noise, if you get the velocity, whole thing, that velocity, that noise gets amplified like anything. Okay. And in the noise, whatever comes, it is always tell you that you can always introduce, assume as a random noise. And random noise means it is normal distribution. And in statistics, how normal distribution becomes so successful? Because any distribution, if you do infinite amount of time, it becomes a normal distribution. That is according to the central limit theorem. And you know that today also, even today, we are surviving based on the normal distribution theory, because it has got some very important physical interpretation that normal distribution will be having the spectral density of constant. So mathematics becomes easy to deal with the normal distribution. There can be other distribution like say Laplace distribution, chi-square distribution, but in engineering sense, if you take the normal distribution, there after that there is something called a tuning parameter. That if you tune, it comes to the nearly accurate. I don't want accuracy of a system to be infinite like 0.0001 type. Accuracy, medium accuracy, then some amount of margin if you can handle. That means as an engineer, you have done your job. I'll give an example. Like a spring mass damper system, which is common to all of us, you know. See, this is my dy by dt square plus b into dy by dt plus k into y is equal to rt. R is nothing but the input to the system, what we call as u. X dot is equal to f into x into u theta. And what is my x state vector? Y and y dot, because it is second order system. And parameters are basically what? Mass, then damping coefficient and spring constant. Okay, and measurement is what? Measurement is my accelerometer. Accelerometer measures whatever comes in the left hand side. That is the thing what accelerometer measures. So from there you have to calculate the position and velocity at the same time parameters. This is called a estimation problem. And I think I have within my knowledge I have clearly told you. Now anybody having any question, they can ask me either now or later. Choice is yours. And see, by using position to velocity, I have computed by using the moving window. That means 5.2 window averaging and all these are standard things in signal processing. And from there, what I have got position, I differentiated. See, still the error exists. But using the so-called Kalman filtering, when I try to compute the velocity, how smooth it is and velocity, and one more is that angle by which the missile is going. These are the physical parameters. So no way you can replace the Kalman filtering as long as you are going to get the derivative of that signal. And derivative of the signal is very important. Based on that, in kinematics, we generate the guidance command, and that guidance command is followed by the autopilot or controller. So, history of the estimation theory, I am going to talk. Okay. First application of ET theory, these are all available in one book called Mohinder Gerwal's book called Kalman Filtering. There all the things are available. So I have shared that book with Mukesh. You can always take it and enrich your knowledge. First application of estimation theory to track the planet, that series by Piaggi, one Italian astronomer, at the end of year in which he missed in January, and after observing he got continuously after 41 days in 1802. That means 17th century. He could track back the planet based on estimation by Gauss. He is the greatest contributor in this estimation theory, and today everything what you think that depends on the least square technique, whatever he developed. Today, whatever we call that optimal control, neural network. Then after that, nowadays you are talking about the artificial intelligence, AI based thing. Everything fundamentally is basically least square technique. And so this is the first application. He could apply this least square, then he could get the planet after 41 days. And what Gauss told, he used that and he got it. So this is the first success of the least square technique. Then after that, 1922, I am going to talk the steps of the statistics by which the science progressed. And these are the remarkable achievements on every milestone. Fisher invented MMLE, weighted least square, for batch processing, mind you, and using Bayes rule and Gaussian distribution. Okay, Bayes rule is basically, you know that from the Bayes theorem, and Gaussian distribution means normal distribution. Then one great person, winner, he was from MIT Lincoln Laboratory. He one of the greatest genius world has produced so far. Winner, first time designed the statistically optimal filter. Again using the recursive least square in frequency domain, you know, to remove the noise from the electrical signal. And that time that was very vital in the Second World War. Okay, and there are all the things in the frequency domain. Then Kalman and Bussy designed the time domain estimation process based on the winner research and using the time domain model, that means state and measurement, in first time in 1958. That is so called the Kalman filtering. He, that basically he used only the theory. And he also told that winner, whatever he has done, there is a mathematics part he has done already. But his contribution is to do in the time domain and to give a overlook to the process in a different way. And perspective is different, but the result is same. But I'm telling you that Kalman's first work, whatever was there, that was lying in the people. He sent it for the electrical journal. People did not like it. They thought that this fellow is a fake character. He does not. He had put a lot of mathematics, and people did not want to go through that. And it was published in the mechanical journal. That means that measurement of signals and all, that is the mechanical engineering. Okay, they published. It was lying in the library for maybe 8 years. So during that time, what happened? Leuenberger invented the observation theory, that observer theory. That means if you can use the states properly from the measurement, you can in a position to give the state feedback. That means already the modern control era has started. In 1964, he invented this observer theory. It became an invaluable tool to apply Kalman filtering from the based on the noisy measurement. Then Apollo space mission came that 1966 and 64, and during that time up to 71 this project started. And researchers in MIT Lincoln Laboratory, they wanted to apply Kalman filter in Apollo space mission for guidance. So those days systems were not like this, like using mainly VTVM. That computer is a very huge computer, so dedicated system was put particularly for Kalman filtering in this what you call vehicle. And today, whatever one computer is there, the same thing today you can do much more important and more complicated calculations in our laptop. You know how the Jamana has changed. So researchers in the MIT Lincoln Laboratory applied Kalman filtering in the guidance loop of the Apollo space mission 66 to 71. It was successful. After that, computers also have become more popular during those days, not from the 1955-52 when the Charles Babbage he invented computer, and from 1971 onward all IBM 370 and all those things became available, and the people started applying in particularly in the computers, and it became a Kalman filtering had become a workhorse since then to today. And application of Kalman filter in the missile system. Estimation of the sensor bias. That means in a sensor, always there will be some initial bias will be there. And it's a physical problem. Nobody can help it. You have to bear with it. And trajectory from the EOTS and radar data. Because when you do the integration, initially there will be some initial value will be there. That is random. So no way you can find out. And aerodynamic coefficients from the flight data. So these are all the offline application. Then for that, the people have used extended Kalman filter for forward pass, and then Bryson Frazier smoother they have used in the offline in the reverse pass, and it is a recursive data processing algorithm and least square. I am not going to talk about the offline application, that is a different subject altogether. So I am going to talk about the online only, because online is much more difficult, and offline once you put this smoother, then it becomes very good. So now, okay, I am just giving some little bit of implication. How come this it becomes so important? If you design a missile configuration, simulation study, that flight test, based on the flight data analysis, you try to get the aero coefficient estimated, and that becomes very important for the control design. And that becomes input from the control design, and control gains and all these things are re-evaluated and tuned to the actual system in the subsequent iteration. So from the flight test, you get the aero coefficient, analytical and wind tunnel also is available. So this gives one more third one, which is complementary technique by which the aerodynamic database you try to correct after the first missile flight. Then online applications, I am talking about the forward pass of only Kalman filtering. That radar is there. From there you try to estimate the states means position, velocity, acceleration, and you get it uplink to the missile onboard computer, and based on that they do the guidance calculation. Guidance means which path it will go, it will try to evaluate, and after that that signal is taken by the control, and control try to follow that path. Basically is a tracking problem or regulator problem. So state estimation from the sonar data for underwater application. Sonar is nothing but equivalent to seeker for underwater application, radar. And one more thing is there in the what you call missile system, that is called seeker. Radar gives the position of the target and seeker gives the relative position of the missile and target. So as a result, what happened if the radar is kept on the ground, the radar has to give the uplink command to the missile. And if it is seeker, it is totally autonomous, and you don't need any third party like radar from Earth to give through the uplink. And what will happen? This fellow will be in the autonomous mode, and it will directly hit the target. So that's why seeker has become very popular, and of course, seeker is very costly also. So cost effect thinking about that, the Air Force or this our users, they prefer always seeker because after some time you use radar. But when the target somewhere comes, missile comes somewhere close to the seeker, you switch over to the close to the target, you switch over to seeker so that it will be in the autonomous mode and it will hit the target. This is in the guidance application. Then navigation application, I'll tell you, it is very, very important. Again, this our GPS will be there. GPS is one more set of measurement, and INS is my plant. So INS outputs based on the GPS, it will be having the bias, accelerometer and gyro bias. This bias will be corrected, and GPS will be having its own clock. So synchronizing the clock is very difficult because GPS has got a very sophisticated clock, but we are having very cheap clock. So that bias generally, and that GPS and INS, whatever comes from the INS comes, that can be removed by fusing the INS with GPS data. Similarly, INS also can be aligned. It has to be aligned in the very first time because roll, pitch, and yaw angles have to be correct. Otherwise, if you keep on integrating, bias will be there. So how to correct it? That also is done by INS, and using the GPS, you'll be in a position to compute initial psi theta phi means your attitude, and this is called a alignment problem. This is one area in which it has been tremendously applied. Then multi-sensor data fusion. You are having one radar, sometimes your other place you are having one more radar, 3 4 radars you have. From there, optimally, if you can they fuse the data, and if you can get the optimal estimate, the redundancy will be there. Suppose one of the radar fails, nothing will happen. Other two are there properly, means it will be taken care of. So multi-sensor data fusion, fuzzy logic, neural network, intelligent control, all these places it will be useful. Okay, I am telling you, this is schematic diagram of the missile navigation using GPS satellite. And if Prithvi class of missile, when there is no INS and GPS, once upon a time, 1980s, at the end of 300 seconds of flight, the error would be at around some 1,000 meters. Then after that, when GPS came, after that it has been corrected. It is in the order of some 30 meters. Instead of 1,000, it comes to 30. So you know that how much important that GPS INS, what you call fusion, by using a Kalman filter. So these are the application area of the Kalman filtering I'm talking about. See, if you think of the historical evolution, I have taken from some book, one NASA TND, NASA report 97647. It will be there in the internet. So first heavenly bodies they use, particularly 1600, that Kepler's equation, heavenly body, that means outside the atmosphere. Then after that, Newton, law of motion. Then Newton again designed involved the calculus. That means ordinary differential equation. These are all dynamics. Only one variable is time, independent, and dependent variables are basically position, velocity, acceleration. So Newton's law. Then 1800, Gauss involved least square technique. That this was a great contribution of Gauss, 1800, and normal distribution. And then people started Fisher, whom I told, 1902 he applied to get the maximum likelihood technique. In the meantime, say this automatic data generation, that is von Neumann machine, it came in 1929 or 31. Then this Kalman and Swerling, these two people, but anyway, people give credit to Kalman because he developed first, so it is called Kalman filtering. Then after that, from 1971 onward, a lot of people started applying this Kalman filtering, and a lot of reports are there in NASA, and a lot of journal papers also came out since 1966 onward. A lot of papers on Kalman filtering. Now in every year at least 200 papers come. And today I'm telling you, 2000 they have given up to 2024 now. So a lot of research have gone in Kalman filtering. Even Based on the Kalman filtering, you try to estimate lot of data. You estimate, then you train a neural network, and people are using AI also. Of course, I have not worked, so I don't want to say anything. But people are using. A lot of papers are there. When you want to apply in a particularly in a physical system, it takes some time. Pioneering contribution in estimation theory. What are the areas? Automobile, oceanic vehicle, aircraft, missile, satellite, and of course robotics, and of course chemical engineering plant also, and governing equation of motion, Newtonian mechanics, and Lagrangian mechanics. Okay, who are the great contributors on this? Frederick Gauss least square, recursive least square. Then Norbert Wiener, MIT professor, and he designed the what I mean to say, he invented this Wiener filter. Then that is in the time domain, the frequency domain. Then after Kalman 1930 to 2016, he applied it in the time domain and the state space method, and he is the third contributor. And of course, other contributors are there. Their impact is not so much, so nobody can replace Kalman filter today. So I am just giving a brief information about what you call this man Gauss. All the informations are available in the net. See, 1855, he was a child prodigy, or he one of the genius scientists world had produced so far. By the age of 8, during arithmetic class, he astonished his teacher by instantly calculating the sum of the using the AP series, first 100 integers. And okay, I am just writing it. I have written here, and you can just go through. All our informations are there in the net, and these are the contribution during his student days. He was only 18 when he constructed a regular 17-sided polygon, the first advance in the matter in 2 millennia. Then Gauss was a mathematical genius. His importance was in number theory, algebra, analysis, geometry, probability, and theory of errors. And he has worked basically on astronomy, celestial mechanics, surveying, geodesy. You know that area, what are the covered here, starting from the astronomy to civil engineering, electromagnetism, mechanism, optics, and actuarial science. That means actuarial science means these are basically art science of area. And I'm just writing that he was a very introvert person, never used to talk to anybody. And Gauss, that Adrian Mary Legender, he in 1805 he published a paper on least square, but he did not give any proof. And Gauss has given a formal proof, and I think we all know about how the least square is done. We all study in mathematics. So Gauss basically introduced that. And Kalman, this is the person about him, what I have taken from the net, passed away in July 2016, basically from Hungary. And he studied in MIT as well as PhD in Columbia University, and passed away in July 2016. It is a mathematical recursive algorithm to remove noise from the stream of data, which increased accuracy. It will never make it zero, but it will make it close to zero so that engineering application apply without any hassle. And last thing is that revolutionized modern arithmetic, automatic control, communication, and system theory. And these are all in the state space method. And I am going to give proper definition of the estimation theory, what basically it does. I have taken from the slides of Professor Ghosh of IIT Kanpur. You are having a dynamical system. X dot is equal to fx into u into theta. Standard equations I'm taking. It will be having the input and output will be there. In control problem, what happens? You give the input and try to get the output and see the output, how it needs requirement with the demanded output will be there, whatever error will be there, and with a minimum tracking error. But this estimation is something different. I'll tell you. Input is there, and output also is there as a measurement. But from there, you have to calculate the state variables, okay, and parameters. So it is a totally inverse problem. So that output y actually matches with the measurement of the system, and by going in the mean path to the noise. Those plots I'll show you later. So input is there, state equations is there, there will be some process noise. Noise will be there. Then measurement will be there, in that sensor is sensed, and sensor model will be there, and noise also will be there. In sensor model there will be some noise and output will be there. So input is some noise is there, and output also some noise is there. What is the noise in the input? I'll give a very good example. When you are flying in the aircraft, you know that when the aircraft goes in the that during the cruise time, what happens? You must be saying so many times that it goes to the turbulence, and some buffeting take place, that you get a jerk. That is nothing but an input. In that it comes as an input, and nowhere, no mathematical sense you will be in a position to model exactly. There will be some approximation and output. So plant also, if you take it, there will be some approximation in the plant. So some noise will be there in the input, something in the plant, and something in the measurement also will be there. So three places noise will be there, and mathematical model cannot represent the realistic phenomena. As a result, what happens? Some amount of noise will be there, some imperfection will be there. That imperfection you have to do by compensating. That is called the process noise. I will come to that later. That is the crux of the Kalman filtering. It is equivalent to gain scheduling, whatever you do in the control. Actually, Kalman filtering and control, they have got very much similarity. There also do the gain tuning, here also you have to do. But Kalman filtering, the plant is basically time domain, and control design, the plant in the frequency domain through the transfer function. That is the difference, but all are same. And application of that: target identification, missile aircraft dynamics, gravitation field, stock market, process control. I forgot to tell you in the first time, adaptive control, because process, based on the gain scheduling, you do the adaptive controlling. And structures, when they vibrate, then how to remove the noise, then economics, the stock market, and system checkout, the human psychological behavior. So many things that Kalman filter can be applied. Apart from this, I know to some extent about the chemical plant. Of course, I have not worked, so I cannot talk about it. Okay. So now let me talk about the Kalman filtering algorithm. I will talk in a very crude sense by giving an example. And equations, if you go through that, automatically you will understand. But I want to cover the physics of the problem. See, I am taking one missile problem on which I have worked. Missile is here, and from this is the target, and this is my missile. Now, mother aircraft where the missile is launched. So once you launch the missile, initially it will be distance around 100 kilometers. So what it will do, up to some 80 kilometers, aircraft will be having a radar. Radar will give you the information of the target, and based on that it will go using a radar filter inside. That is also a Kalman filter. Okay, then after that, once you go somewhere close to the target, around some 20 kilometers range to go or something, it has to, then seeker dynamics will come. Seeker will be opened, and seeker will keep on searching the target. That may take not more than 20 seconds. Okay, then after that, the all the control will go from the radar to seeker, and and the system becomes autonomous. So when it happens, this fellow mother aircraft will push off from the enemy, and once it is in the autonomous phase, you will go in the when hit the target. So how many filters are there? One is the mid-course phase radar filter, and terminal phase is the seeker filter. Those two I am going to discuss. And I am going to discuss only the results, but equations I have written down. But you can, once somebody is interested, he can always find out. And I have given some papers also. Any doubt, somebody can contact me. Why the estimator is used? Because this is my autopilot and this is my guidance law. So estimator, what it will do, it will take the radar noise from the radar, noise from the seeker noise, it will be there, and seeker data it will take, process it, and using the Kalman filtering, that means seeker measurements will be there, prediction will be there, update will be there. From there it will get the state variables, and in the observer mode it will go the input to the guidance law. So as I told you, the Kalman filter is used as an observer. And derivation of the Kalman filter equations. See, some of the books I have given, and all these books also I have supplied. Actually, to be very frankly speaking, if you are a beginner, best way of learning is the make a mistake and learn. And some of the mathematics, some of the codes also I have given. And you need linear algebra, probability, missile kinematics and dynamics, preliminary knowledge of system theory. And this from, though people used to teach in what do you call postgraduate level, people used to teach in particularly EC department once upon a time. Nowadays, in Institute of Science, they give in the aerospace course, but anybody can go through, and it can be open to any engineering discipline. You need only these things, and physics of the problem you learn by making mistake. Okay, I am giving you the equations. I'll give an example that will be better. These are my state equation. They are all nonlinear equation. This equation very familiar to you, and y is the output, and z is the measurement, means y plus eta. This is my noise, and input will be having also a noise, and by approximation, I'll highlight what are the sources what gives the noise. Okay, I am writing that Kalman gain, it will be propagation, then update, and based on that, it will go. So these are the equations of the Kalman filtering, but these are all jargon. I will tell you the basic physics. And if I can convince you with the physics, then you will understand. This also I'm telling. This will be basically predictor corrector algorithm. Predicts. This is the prediction algorithm. That means differential equation. So you solve the differential equation for one time delta t. Then after that, there is something called variance will be there. Any statistical system will be having the mean and variance. So variance in the scale, what I mean to say, in the multi-dimension is called the covariance. So covariance also you propagate, and then after that you'll be having the measurement. Based on that, you correct. There is something called Kalman gain, and with that you try to estimate the state also and covariance also. And this is the gain. Okay, so this is my real world, and this is my filter world. Okay, so these are the equations are there. That's all. You have to just do the coding judiciously, and once you make a mistake and correct it, your basic fundamentals will be clear. Now, let me give an example. I belong to Hyderabad. So I am giving an example of Hyderabad only. Anybody from, anyway, from one place to other. Yeah, from here, I am giving from DRDL to where I work, and particularly Secunderabad, wherever the train goes. Like this, you can extrapolate between Trichy and Hyderabad. Say you are going by a train. Once you start from the station, if you calculate the exactly, some element of error will be there initially. You cannot find out exactly. Okay. And from here you start. So error, what will happen over the time, it will keep on propagating. You go to the next place from DRDL, there is a place called Saidabad. You go to Saidabad, some error has come, you see here. Then what will happen, once you give the correct information with some amount of accuracy, it will update. That means with this knowledge, it will position to update it. So instead of coming exactly to Hyderabad, some little bit different place will be there. Okay. Then again from here, you go to one more place called Koti in Hyderabad. Okay. So Koti, once you go, it will not be in a position to go to exactly some amount of error will be there, because sensors will be having the error. You can't help it. Okay. So then after that, you give one more update by another instrument, say by using radar. Radar is an instrument by which you generally give the update. Then again it will come here, and again it will go here. Koti, there is something place called RTC crossroad. So there you update. Everywhere the loop comes means you are giving the external information. That is also noisy. But what will happen in the process of least square? It is basically recursive least square. So noise from both the elements will go. Okay. Then after that, you go to Secunderabad. And Secunderabad also, again, you do an update. You get the information. Then after that, you go to the airport called Begumpet Airport. So whenever I did this, right, the wrote this thing long time back, around 15 years back. That time, Begumpet was the airport. Okay, so from that is the place you have come. So instead of coming to the airport, it will come to some other distance, maybe around some 100 meters, 200 meters. So once you go there, without any hassle, you can just come to the airport and take my, you need not have to take some auto or something to come. So whatever, without any update, the distance would have been this much. So that much amount of thing you are going to compensate by using the Kalman filtering. And that is the importance of the filtering here. And unless you remove the noise, you know that had you removed the noise, it would have been come to exactly to Begumpet airport. But some amount of residual will be there, and we are basically solving a engineering problem. So instead of Begumpet, it will go around some 200 meters away in other direction, it will correct it. So learning basically based on the thing is this Kalman gate. Okay, and correction is based by x and p, and by using this formula. And when you try to go first time, this is called the prediction. These are the one set of equations, one equation, then other one, this is the second equation, and basically gain calculation is this one. So how many equations is there? 5 equations. That's all. And you have to do in the recursive way so that you can finish up within say 10 milliseconds. In today's computer, in the real time, if you do, I don't think doing whole this job, it does not take more than 2 milliseconds. Okay, so this is the block diagram of the Kalman filtering with state and measurement. This is the essence of the filtering, and I am not going to discuss about the equations. Once you understand the physics, automatically equations will come with a statistics knowledge. And you know that your knowledge need not have, but you can always go through the book and can find out what is the meaning of mean and variance. And with that, you have to go with some amount of matrix algebra. So I am going to talk two cases. This is the theory part. I have told two cases. One is the radar filter, another is the Sarkar filter. Radar filter, you will be surprised to know that this has got very much link with the physics, whatever is studied in class 12. And, so how much amount of fundamental level that people have gone and developed, So that's what I mean to say. Ultimately, the filter is one part. I'm going to talk about the plant now. Constant velocity, constant acceleration, constant jerk. I am very sure you will come to know what it is, and you know everything. Okay. So when I derived first time and gave, then over that I tried to make the improvement. I feel that if I write like this, audience will be in a position to understand. Because constant velocity means what? Velocity is constant. That means what? Kinematics x1 dot is position is equal to x2. Okay. And x2 dot is equal to 0. That means velocity is constant. X1 goes like this and x2 becomes constant. So you try to calculate this by integration. X2 is equal to c1, x1 is equal to c1t plus t2. What is this? This is nothing but S is equal to S naught plus U into T. Whatever you have studied in our mechanics. So the same thing are writing in a casting in a different way and doing the integration. And now what is the error you are getting? Because this is for a particular system where the velocity is constant. Velocity cannot be constant. So S is equal to S naught plus ut and put the what do you want Taylor series fx plus h is equal to fx plus h into f dash x. It is the same as this plus higher order terms. And that is the approximation I'm going to do for a nonlinear system. Linear system is 100% correct, but nonlinear system, some difference is there. We have to compensate somehow. I will come to that. So S is equal to S naught plus ut. Come on, let us write down the equation with the disturbance. That means in a stochastic form. See, x1 is equal to x2 and x2 dot will be 0 instead of some noise will be there. So just you see, let us write down in the A form, state space form. It comes like this, ax plus bu plus gw and y is equal to x1. So measurement is this, x dot plus y, ax plus bu, y is equal to cx. The standard form. Or here they are writing hx plus eta. Here also some noise is there. So it will be it will be written in this form. So with this form, you have to design a Kalman filter, constant velocity. Let me go to constant. I have written this, and whatever amount of error comes, no, that will become like this. And you have to calculate the variance. So variation with a little bit of algebra, if you do what you call that is called the process noise matrix, it will come like this. I have written here, and anybody interested, he can go through. It will be there in book of journal paper of Singer or some book of what do you call this book also will be there. Candy also it will be there. Okay. So now constant acceleration. This was invented by Singer, AES 1974. Position, velocity, acceleration. Position to velocity, velocity to acceleration is a constant and acceleration is a constant. So let us take the kinematic model. x1 dot is equal to x2, x2 equal to x3, x3 equal to 0. So now let me compute by integration what will come. S is equal to S naught plus ut plus half into at square. This is again this thing what you study in your 12th standard. And now if I want to model it, you put some noise. Here is the noise in the state model and measurement model also this is a noise. So these are standard state space form. And for this also, if you want to try to calculate the variance of that noise, this will be like this. This I have taken from this Singer's book was there, but after that Barcelom also has written. So those books I have given you, and this is my tuning parameter in Kalman filter. This value you have to put, and according to this you have to see. And once you see the output of the filter and your measurement, they match in a least square sense. That means my tuning is correct. Now, it is a paper by Professor Mohapatra and Mehrotra from one ISC faculty and one student. This is the constant jerk. Position, velocity, acceleration, jerk. You take the kinematics, keep on integrating. What will happen? S is equal to S naught plus ut plus half into it square plus 1 by 6 into j into t cube. You know that this equation is there in the Hesse Verma's book in intermediate physics. So ultimately this comes this, and there is no need of taking any model more than that. You are going to just increase the models and it is not going to do any effective solution or improvement. So this is the place people have stopped till today. So fx plus h is equal to, you just keep on expanding, then after that the noisy term comes. So what the noisy term comes, so this is basically the kinematics and model and measurement model. And that also is Q is this. So whatever was there in the constant velocity, constant, it's the same way you can calculate the measurement noise covariance, process noise covariance of this. You put this value and try to keep on tuning manually. Just like you do the PID controller manually tuning and all this thing. People have done automatic, but my experience, manual tuning is the best. So I have told what constant velocity, constant acceleration, and constant jerk. So near perfect model in literature. So these are my model, but model cannot be in a position to mimic the reality in the best possible way. Impossible. So you have to use that compensating term called Q. So by proper selection of the P naught means covariance means initially Q and R. R is the measurement noise covariance. So looking at the measurement signal, if you take peak to peak variation divide by 6, that means 3 sigma that way this way. Then after that you make it whole square, that becomes my R. And Barcelona had proposed a model called NIS cost function. If you can putting the value of the Q properly, then after that if you can calculate this matrix, then if it becomes the number of channels, then your tuning is correct. And ultimately you won't believe you, once you take the simulated data, exactly it will come. Suppose my 3 measurements are there, it will come to exactly 3. But the flight data is there, it will not come 3, it will be coming around 2.8 or 3.1, and you have to bear with it. Because flight data, what happens, that Gaussian noise is not there. Some other correlated noise will be there. But filter works properly. Whatever amount of error is coming by proper modeling, not modeling, that is compensated by the Q matrix. By proper modeling, you can do your job nicely. And today's world, there is nothing better than this is available. So that's what I mean to say. For so many years, Kalman filter is working properly. After that, some other filters have come, but nobody is in a position to replace the robustness of Kalman filtering. So let me take an example. I have given how to choose R, Q and all, and I don't have much time. I have to finish up by 7:15 as Mukesh has told. So I am going to talk about the radar filter, open loop design. Once you do the open loop design in the MATLAB, then after that you have to put in the closed loop with the 6 degrees of freedom model. The papers are there. I have just given it. You can just go through. We use MATLAB basically because it is easy to implement, particularly for an Akash type of system where the aircraft is coming from the aircraft, the signal comes here. That means transmitter, no, receiver. Receiver gets and the transmitter it transmit to the missile for command guidance. So this is how it works. And exactly the same thing, radar is there. With that you use an observer and give the input to guidance signal, and that gives the commanded acceleration, and acceleration will be tracked. So it is basically state feedback system to the guidance law. And these are the areas, most important papers on this area, what you call over the years I have just done here. And measurement data will be there in 100 millisecond update, and target can go up to 6 to 8G. So it becomes a nonlinear filter, and you have to use extended Kalman filter. So filter tuning by optimize the normalized innovation sequence, you can get this what you call Q, and you can use the GA also. And see, the papers have given, but I'll tell you from my experience, manual tuning is the best. Once you do the work for some time, now you get a rule of thumb, and that will be in a position to do it. Practical application estimated to be used for the real time for guidance command generation. This is my radar, and this is the target. This is my range to the target. This is my target, azimuth and elevation. So I have taken on all the directions the what you call state equations: x direction 4, y direction 4, z direction 4, and range, azimuth, elevation is a function of x, y, z. So this is basically from the kinematics. So let me design the filter that J is equal to 1 by n into nu transpose HP H transpose plus R. So here I have done in a algorithmic way because to be very frankly speaking, my PhD guide is very particular about this algorithmic, what you call method. But after that, I have seen myself when you do know, instead of algorithmic, basically by hand tuning is the best. And this many people have agreed also with me that you don't have to do the algorithmic way of Q tuning. So now with the simulation results I'm showing you. So one particular area, what will happen that initially the window size by which you are going to smoothing, it will go about very small value to it will become 3 for a certain domain. Then after that you will keep on increasing. So you particular take any Q value from this area. And you know that when it is constant for so much of time, that means there is a lot of variation within Q. Like a gain margin, phase margin is there in control. No, so here also a lot of variation is there. Within this, the filter will work. So you know what happened, that X dot I have given, and this much amount of error and estimator and true. X dot, Y dot, Z dot for a 7G maneuver. And acceleration also you can position to compute, but generally in our guidance till now we are using the acceleration, but we are not in a position to do anything better without acceleration. So till now in the missile complex we are dropping the acceleration. We are not using the acceleration term. And after that you pass it through a low pass filter, the innovation, that oscillation becomes less. So you know that when you try to use it without what you call, you know, without using the low pass filter, you put the low pass filter, this becomes quite smooth. And once the signal becomes smooth, my command also becomes smooth. And latex command, when it goes as a smooth, it does not tax the actuator, because actuator it goes as a noise, you know, actuator also will give lot of power, and always better to use a smooth signal to actuator. So this is my what I mean to say, what I have done the radar filter. Similarly for the seeker also, seeker filter design, you know, that I have to finish up by 7:15. Exactly in the same way. This is my seeker noise and seeker data. Then after that, it will come to this is my observer. Output of that is coming to the guidance law. Then it will come to commanded acceleration by in the same way. So seeker, what are the measurements available? Schematic diagram of the seeker. Seeker is a missile and this is the target. It will give you always the relative range. This in between missile and target. In radar, what it used to give? It used to give the absolute range of the target position, and it will go to uplink and you have to subtract. And based on that, you have to generate the guidance command. But seeker, what happens? It is kept in the missile. So missile keeps on rotating, this fellow also keeps on rotating. It has to be kept in a gimbal so that it will not be rotating inside the gimbal. It has to be in the fixed position. So a lot of frames are there and frame conversion has to take place. This is a part of kinematics and I need not explain. If somebody works in the area of some robotics and all, there the kinematics is very important. That is also very similar to this. So problem definition is my measurement data of the relative what you call range rate, and the gimbal angles means the angle where it is kept. Now it will keep on rotating, and gimbal angle rates are the seeker measurements. And I have to get the relative position and velocity and acceleration. What are the constant? Data is at 100 millisecond interval. Data is a very noisy and there is no, what I mean to say, it cannot be made as a Gaussian noise. In between, what will happen? It will having a glint noise, thermal noise. Then sometime data will come or not come, called eclipsing. There is a aperiodic data loss in LOS rate during the eclipsing. So these are the constant, and using a standard Kalman filter, it has not, it has got some definitely what you call not good tracking, very good tracking, but the type of tracking we have done, once you do in the 6D and try to see, it comes miss distance, what is the parameter to calculate how much is the distance at the end, that becomes quite good. So with this being a non-Gaussian noise, assuming it to be a non-Gaussian noise, we are in a position to get successfully good result. And I am going to give the seeker how it works, because seeker, from seeker also some noise you will get from the track loop. And now you see, this is my true measurement and this is my noisy measurement of the gimbal angles. You just see noisy measurement. Definitely it is not Gaussian. Towards the end becomes very big because of the glint error is coming. Okay. And measurement and true, this is my LOS rates. You know how it works. You just see this is the true and this is the noisy signal. And gimbal angle also true and noisy. I am showing you. And R dot is more or less Gaussian range rate. And so range rate all are available. Sometimes range rate is not available during eclipsing zone, and non-eclipsing zone it is available. Okay, so that is a variably. Sometimes it will work and sometimes it will not work. That LOS rates. So Kalman filter formulation, like we have taken the state equations there. Here is the relative state equation, and this is my control input. And measurements, I am giving some what you call algebra, but they are all nothing but the transformation matrix, and that you learn automatically. So you need not go in details. So I am going to give you the results. All range data will come and they will come with a noise. So 4 measures and 6 measurement like this. So it will be 10 millisecond interval, it will do the job. So you will do a nonlinear transformation. You go from LOS through LOS frame, and then you go to body frame, fin frame, and energy ball frame, and all the transformation you have to do. They are nothing but the mechanics part. Okay, I have given the value of the PQR and comparison of the radar and seeker filter in a closed loop. This we have done. So this we have written a journal paper. You can always go through whoever interested. And we am going to take a engagement scenario. See, for that engagement, once you see the LOS rates, see how beautifully it is the noisy data and all the noise has gone out. We have been in a position to take out most of the noise, and you see the mean is, if you take the difference between the two, zero, it will be more or less zero mean and very small value. Here it was minus 30 to 30, here the difference from minus 2 to plus 2. So all these things we have done. And then after that, pins from the control, what it will give, the red thing is basically with the EKF model we got. And if we put a low pass filter, this will be like this, control deflection. This goes in the actuator. And like this, if it goes, no, actuator will drain the battery within no time. But red one, when it goes, it is quite smooth. That's what we want. And for that, you need a very heavy duty actuator because bandwidth becomes more. And here, 20 hertz to 30 hertz actuator will be good enough. And delta dot, when you compute, you see this is the noisy, and from the Kalman filter you do means derivative calculate, this comes down so much. So much of signal to noise ratio, it has come down. It has become very high. And after that, you try to calculate the accelerations, it will go like this. So this is the total acceleration profile by which it will be in a position to till the end. What will happen? That this is my acceleration profile. This is my demand, and this is the executed. Demand is the green line, and executed the red line. You know that noise is quite less because you have removed the noise already by using a Kalman filter. So that's why the noise is very, very less. And gamma dot, that means Partsworth pitch lane LOS rate that is required for guidance. And the same thing with the radar we do. Then what will happen? This true and estimated. Okay. 100 millisecond for EK update in the radar. And seeker, it is some 10 millisecond. How it has improved, LOS rate. And we have given in the paper in details that how much is the latex comes in. This is the seeker and this is the radar. But radar, what happens toward the end, there is a distinct jump because my range becomes zero. That particular thing becomes infinite, and it will be difficult to calculate because of the singularity problem. But seeker, this does not come because it directly takes the difference of the angle. So that is less. So the radar, what happens that it goes up, and here it does not go up. So one typical trajectory I have shown. This is by Partsworth and Eveder. This is going to hit the target. And this is the thing. Ultimately, what happens? You have to do the Monte Carlo simulation because once the noise comes, uncertainty becomes more. So all the parameters, initial condition, that aeroderivatives and all those things, you have to use a normal distribution and you have to do a Monte Carlo simulation. And once you do the Monte Carlo, you have a 500, 700 like that Monte Carlo or 1000 Monte Carlo you do. Nowadays, computers have become very fast, so they even make 2000 Monte Carlo also. And not a single one should go out of the bound. So that is the Q factor I have taken for radar as well as seeker. So Monte Carlo simulation I have done, radar and seeker, and misdistance, if you see, then you see 9, 13, 25. Seeker, it comes 1 and 8. That what I mean to say. Here, one is 10-second update, and radar it is 100 millisecond update. Okay. So I have given a comparison between radar and seeker. So you can just go through it, and I don't have much of time. So I see at the end what I want to say. Seeker is more preferable, but seeker is more costly. And radar will be much cheaper, but at the cost of what? Once enemy jumps the radar site or enemy bombs the radar site, then missile is totally blind. But whereas the seeker is there, missile cannot be blind because seeker is on board. So everybody, even our users, they all want the seeker-based guidance, but not the radar-based guidance. But of course, so our Akash missile is radar-based and Astra is seeker-based. Nowadays, missiles all are seeker-based because of this. Now I will show you the some of the flight test result, because one algorithm we develop, it will be basically successfully done by flight tested, means that means your algorithm works. See, measurements residual and all, from there I have tried to calculate the R matrix. You see, this is my radar and this is my estimate and measurement. If you find out the difference, it comes like this. So in terms of 1,000 around 10 to 12 kilometer, but here it comes within 0 and 30. And you see that it is not Gaussian, but somewhere what you call means will be very small, but it is not a Gaussian noise. But it works because when I've given the Q, no, model uncertainty is taken care of. That's why the Kalman filter is so popular. Then the flip test to have done and measurement, and this how it is matching. So this is my error. And gimbal angle also. Actually, our simulation, the model was there, what the Russian people gave. In the flight, the error level has come down. That way we are happy. Flight performance is better. And there are the gimbal angles and LOS rate. Now you see LOS rate, how nasty it was. Now nicely, smoothly it has done by after filtering. So this is the importance of the filtering in this missile dynamics. Otherwise, it will give more amount of oscillation in guidance, and ultimately it will tax the actuator, drain the total power, and mission will be jeopardized. So this is the ultimate thing I have shown. So now I'm going to conclude now. I think I'm within the time. Evolution of the estimation theory I have told from the beginning. MATLAB is a tool for real-time state estimation. Nowadays, the people, they are doing by Simulink. Of course, I don't know much of Simulink, so I have not used. I use only MATLAB. Design the radar estimator by using MATLAB. Seeker estimator also using the MATLAB. Why you use MATLAB? Because matrix multiplication, you will not make any mistake. Second thing is that coding is very simple. But after you design, ultimately in the C code, you have to go to the OBC. That time you have to use the C code. So closed loop validation by radar seeker estimator. Monte Carlo simulation for robustness of the system. Comparison of radar and seeker estimator. Then flight test validation. So these are the things in a nutshell I have covered. And anybody is interested, they can always reach me. Okay. So my other contributors, any job cannot be done alone. And I don't believe in telling that I have done myself. It doesn't make any sense. Here, my contributors are basically mainly Dr. Vatsal. He was my organization guide, and he was a mentor for me to come to this area to do the work. And this is the person. Then I did the research for the PhD under Professor Anandasanam. He is my guide. I mean, through whom I have got the PhD. And this work, some amount of contribution was there towards the end by Professor Radhakant Parhi also. He from ISC. Ultimately, if not on this, Mukesh is the person who gave me the chance to talk to you. I thank you very much for your patient hearing. Then after that, if you have any question, you can ask me if the time permits. I was told to finish by 7:15. I have finished by 7:05 or so. If somebody wants, he can ask me the question. I have finished my job. So thank you very much for listening to me. Any question means I am ready to answer. Any question?
Participants, if you are having any questions, please ask.
No, actually, this is an interdisciplinary topic. So nobody knows initially when he joins the organization. Over the time, you pick up. And your fundamentals of mathematics and coding should be clear. That's all, nothing else. Rest, everything depends on the interest. This is not only true for me, for anybody.
Sir, whether this Kalman filter can be used for any prediction, like tech prediction, ionospheric tech prediction, as well as ionospheric measurements like that, sir?
You see the papers first. I can tell you the papers I have seen, because I have never done any work on my own. I always refer to the papers. Wherever some model will be there and measurement will be there, it has to work. INS GPS integration, I know, because a lot of papers are there. And ionospheric model, yes, I think it will be there, because one chap called Anandaraj, he was doing work under Professor Ananthasaram during 92 to 94. No, 2002 to 24. He was doing something on ionospheric prediction. You ask Soma sir, he must be knowing his whereabouts now.
Yes, sir.
It can be done.
Yes.
Wherever my state is there and measurement is there, and these are all kinematics. So state will be known. So definitely it can be done. But I request you, at least one or two papers, if you go through, no, you are very confident of what you are doing.
Yes, sir.
You can do.
Any other questions? Sir, currently you are working with the hypersonic missile target prediction.
No, actually, right now working for, I'll tell you, it is one step ahead of Kalman filter. That is one high-speed target is coming. More or less, we have finished now. It has been flight tested. So there are three models I told you: constant velocity, constant jerk, and constant acceleration. Depending on the situation, when the missile is traveling very fast, it will switch over to the jerk model. And when it is cruising, it will switch over to the constant velocity or constant acceleration. So it will do the model switching so that the Q becomes that process noise tuning becomes to some extent automatic. So it has to do, see, for one particular zone of flight, one model will be valid. So dynamically, you should try to switch over from one to other to give the best estimate. So that is the work I'm doing. And flight testing, we're expecting somewhere in the month of April, let us see. So it will be coded in, it has been coded in the real time, and other trials are there. So now testing is going on.
Sir, what is the main difference between Kalman filter and extended Kalman filter, sir?
Oh, achha. Kalman filter generally what tracks the linear system, but extended Kalman filter will track the nonlinear system because you are going to linearize over a particular time. So any small time, what happens if you do the linearization, nonlinear system becomes linear. It is something like this. Control design, when you do no, we use the linear control, but we try to do it for any nonlinear problem. How we're doing by gain scheduling. So similarly, in the Kalman filter also, straight line, if you want to track, no, you don't need Q. Automatically it will track. That's the difference. And whereas in a path which is not straight, because of the, that whatever errors you are making, so that we're doing by the Q compensation. So in that case, you have to use Q. And in a linear system, we don't need Q. And non-linear system, if you don't give Q, no, it will divert. It will not work. That's the difference.
Sir, already lot of work has been done in the Kalman filter. What new we can do in this?
I'll tell you one thing that yes, a lot of work has been done, and I can tell you what the people have done the pioneering significant work. One is Kalman himself, and one more man named Singer. I wrote his name here, and one more man called what do you call Barcelona. That model switching. After that, I don't think anybody has worked something new. We are all applying for a organization problem. What new thing can be done? See, I can very easy to say, but doing is equally challenging. That is, now we can think of this AI-based Kalman filter tuning is coming, and lot of papers are there. But whether you can do for a real life system or no, I have got a feeling you have to do research at least for 1 or 2 years. Then only you can say. Because just like that, it will not come. You have to, AI, you have to know, then there is something called particle filter. By using the AI, you are in a position to do. That's what the people are basically telling. So in that case, what happens, the what error comes down, no, that will be minimized. And people have reported also. So that is something new one can think about. But you have to use the AI technique. And you need a very high-speed computer. And nowadays, I think those computers which are using AI, this type of parallel processing systems are available. This is something new one can think about. But saying is one thing and doing is something. So I should not tell that the job will be very simple. See, I don't want to say simple or difficult. It will be more involved. It will be more involved. I don't want to say it is difficult because people who are doing, they are human being only. They are not great people. See, when they're doing, they're definitely greater than me. But these things working means you need a dedicated person doing the work. Lot of time, and your organization should be ready to spare the time for you without disturbing in the day-to-day work. This is our organization problem. Organization problem means any project director wants to give the problem to you today, they will want to get the result yesterday. It is possible. I can tell you, if you want, what are the areas? One gentleman in USA, he's an Indian only, Professor P.K. Menon. He has been working on that. So I can give you his mail and you can contact him. Or whatever work he has done, he came to ISC for some giving a talk. Whatever materials he's given, I can share with you.
Okay, sir. Thank you, sir.
Okay.
Right. Participants, any questions are there? Sir is expert in Kalman filter. I know.
Arey, Mukesh, you don't tell gig. I have to survive and I have worked. That's all.
Okay. Now it's the time to announce the vote of thanks. I request sir to tell the vote of thanks. Dr. G. Sivakuran.
On behalf of Organizing Committee of the Atal FDP program, I am deeply honored to propose the vote of thanks for today's session. At the outset, I extend my sincere and profound gratitude to Dr. A.K. Sarkar for delivering an exceptionally insightful, intellectually stimulating talk on Kalman filtering and its model as well as various applications. His depth of expertise, clarity of exposition, and ability to connect theoretical foundations with the practical applications has greatly enriched the learning experience for all participants. Sir, your session has significantly enhanced our understanding of this pivotal estimation techniques and has encouraged us to further explore its wide-ranging applications in research and engineering domain. We are truly grateful to you for taking the time to share your knowledge and experience drawn from an illustrious and impactful career. I would also like to express our appreciation to all participants, faculty members, and technical staff and members of the organizing committee for their active involvement and support, which contributed to the smooth and successful conduct of this session. Finally, I thank each one of you for your presence and engagement. We look forward to many more such meaningful and enriching interactions in the future. Thank you.
One sentence at the end, 1 hour and 15 minutes talk. I cannot share everything. What happened? I have given the books, soft copy, and anybody interested to take them. And I have given a tentative radar and seeker filter just for the sake of explaining and giving a talk. Okay, so these are sample codes I have given in the MATLAB. They will work 100%. So that is not even a missile system. So I have taken out and made it tailor-made for this type of application. I have given both the radar code and seeker code. So please go through that. Anybody interested? So he won't have to start with the scratch, because nowadays things are, whatever I'm giving, they are all available in the net. Anybody starts working in this area, you go through the course, understand, and ask me, I'll answer you. Because as long as this type of Google Meet and all those things are there, sharing is not a problem. Anybody, student is interested or something. Okay. I also thank you to Mukesh and you both, and for giving me the chance to talk. I thank you very much. But any person, if he's interested, I'll try to give the information in the earliest time possible. Thank you all listening to me.
Thank you, sir.
Thank you.
Sir, kindly stop sharing your screen, sir.
I will.
Dear participants, now we are entering into the session 10. Now I request Dr. S. Kritika to introduce the chief guest.
A very good evening to one and all present here. I welcome you all for the Day 5 Atal 6-Day Online FDP program on Navigation with Indian Constellation, Opportunities, Challenges and Future Developments. It's my privilege to introduce our esteemed chief guest, Dr. Ramesh Raju, a highly accomplished aerospace engineering professional with more than 27 years of excellence in systems engineering, avionics, and product lifecycle management. He currently serves as a senior engineering manager at Honeywell Aerospace, where he leads a global in-service engineering team supporting critical avionics systems, including FMS, data link, radar, TCAS, and EGPWS across major platforms such as Airbus and Boeing. His career reflects a strong track record of technical innovation, stakeholder engagement, and cross-functional leadership with multiple awards recognizing his excellence in delivering complex aerospace solutions. Earlier, at Hindustan Aeronautics Limited, he managed flight test instrumentation and post-flight data analysis for rotorcraft programs such as DHRUV, Mi-17, and Sea-King, contributing to aircraft certification through telemetry and tracking solutions. His career began at DRDO's LRDE, where he worked on software digitization for EMI/EMC standards in airborne platforms. Academically, Dr. Ramesh holds a PhD in aerospace engineering from Jain University in 2023 and MS in software systems from BITS Pilani in 2000 and a BE degree in aeronautical engineering. He is an in-course certified systems engineering professional with additional credentials in project management, ITIL, service management, Lean, and Six Sigma. His scholarly contributions include 4 international publications in avionics, navigation, and satellite systems. Known for bridging technical depth with strategic leadership, Dr. Ramesh has a proven ability to drive innovation, resolve complex technical challenges, and deliver customer-focused aerospace solutions on a global scale. With great respect, now I invite our esteemed chief guest, Dr. Ramesh Raju, to take over this session. Sir, please.
Thank you, Kritika, for the great introduction. Do you able to hear me?
Yes, sir.
Yeah. Thank you, Dr. Mukesh, and all the faculty members who is attending this session. It's a great privilege to interact with all academicians like you, and whatever extent possible, I will try to share my experience and the details about the topic. The topic which Mukesh asked me to present is the positional error correction for use on DGPS. So I think this is session 10, and I know you all last 5 days, including today, you are all going through various sessions talking about GPS, NAVIC, IRNSS, all these navigational topics, and some of my contents may repeat few of them, but I will ensure going through the repeated content faster and focus on the topic which was asked me to present. You can always stop me if you have any question, and I am ready to answer you. Okay, is it fine, Mukesh, Kritika, and others?
Yes, sir. Please, sir. You can share your screen, sir.
Let me share my desktop. Yeah. Let me know if you see my desktop or
Yes, sir. Yes, sir.
see
It
my
is visible.
presentation. One second. Let me give me a minute. I will reshare my stuff. It is 1 second. I'm having an issue to full screen. Let me desktop. Yeah, let me know once you see the desktop.
Yes, sir.
You are seeing, right?
Yes.
Okay, sure. So differential NAVIC, when you talk about differential NAVIC, program position error correction is one of the main topic what you will discuss on this. So the overall concept is differential NAVIC. And DGPS or DNAVIC, the concept wise both are same. So only the difference between GPS and NAVIC, GPS is a global positioning navigation satellite system, and NAVIC is regional navigation satellite system which is developed by ISRO in India, and the footprint, the NAVIC and GPS has entire globe footprint. NAVIC has footprint 1,500 kilometer across the Indian region. So that we can know. I think some of the previous sessions you would have listened to them. But anyway, I will take few contents to repeat, but I will not spend much time on the repeated contents. And you already listened to Dr. Garudachar Raju, visiting professor of Jain University. He was my guide and supervisor for my research in Jain University. You would have touched based on few of the contents which my research, and he told me to take from. I think he touched upon the concepts, but I may go through some of the details, technical details to you. Okay. So let me go to the. Let me minimize this. How to do this? Oh. Give me a minute. I think. Yeah. Okay. Sure. So we know across globe we have multiple global navigation satellite systems and the regional navigation satellite system. In this slide, I am trying to show the comparison between all the currently available or active GNSS and our GNSS stuff. Baidu, Galileo, and Baidu, GLONASS, and GPS are the global positioning systems which covers entire. In fact, I think Galileo too, entire globe as a footprint and try to provide the position information to entire globe. In this table, NAVIC and QZSS are regional navigation satellite systems. NAVIC covers major part of Indian subcontinent, and QGSS covers Japan. And we know we have the number of satellites and which altitude the satellite constellation operates in each GNSS system is given here, and the operating carrier frequencies for each of them, and specified accuracies of each GNSS system is provided in this table. If you notice, the NAVIC is the one, the NAVIC satellite constellation is the one which is higher than any of the except QZSS, higher than all the currently available GNSS system. It is operating at 36,000 kilometers. And NAVIC has 8 satellite operation satellites, which in which 3 are operating at geostationary geosatellites and 5 geostationary orbit satellites. And mainly the operational carrier frequency of NAVIC is L5ES. Whereas if you compare the GPS, we have L1, L2, and L5 carrier frequencies, and it has 24 operational satellites across circling around the Earth of six orbits. And ideally, it has 30 operation satellites 24 is the required, and rest of the other 6 satellites will replace the inoperative ones whenever it is needed. And I think you already know any GNSS system will have 3 segments: space segment, control segment, and the user segment. So control segment will take care of the uh, maintenance activities of each satellite. Whenever something is going bad, they will replace the other satellite, and they will see health of the each satellite, whether everything is fine, the clock, how all these control segment will take care of that. And space segment will be part will talk about the footprint, number of satellites, what is the format, what data it should transmit, which carrier frequency it should have. And then the user segment, or the segment where end users will use this satellite information and try to come up with the position details on the place wherever they operate. So that's the broad description of this slide. Anybody have any questions? You can ask me. This slide, I'm giving it to you to show you the different GNSS and what are all the difference between each of them, and how NAVIC is unique compared to them. Okay. My next slide, the satellite segment of GPS and the IRNSS, the footprint where actually the system operates. If you look at the left picture, where the GPS 24 satellite operates in 6 orbital planes around the globe, it has a capability to give you the positional information. And when we compare at the right side, we have the IRNSS footprint, the coverage area. The dotted circle represents the coverage area where IRNSS can provide the positional accuracy less than 20 meters, less than or equal to 20 meters. And the dotted square indicates the coverage area where IRNSS provides the accuracy of 20 meter and above. I may repeatedly use IRNSS and NAVIC. Concept-wise, both are same. It's only a name difference. IRNSS is Indian Regional Navigation Satellite System, and the Indian government gave that NAVIC as the name to that. So both are same technically. So I will be repeatedly using it, but that is the understanding about both of them. Okay. I think you are all in these 10 sessions. I think you are all discussed mainly about NAVIC and other navigation system. This slide will give you what is exactly NAVIC and what exactly ISRO tend to come up with this, when it is started, and what for it is. So this as NAVIC is nothing but navigation with Indian constellation. And it started in 2018. It became operational from 2018, and mainly used for position occurrence, mainly used for the navigation. Okay. And this is another fact sheet of IRNSS, which the specification what ISRO is defined. 7 operation satellites, 3 geostationary and 4 geosynchronous satellites. I think the previous slide here, we can note here the 3 GEO satellites are on top of the equator, and the 4 geosynchronous satellites, 1A, 1B, 1D. You can notice it is rectangular. In the figure of 8, it will circle around, which are all geostationary, geosynchronous orbit. Okay. So going back to the fact sheet. And the operational orbit altitude is 36,000 kilometers. The total estimated cost, which is 20, when it is planned in operational 2018, is 1,420 crores. But now it might be become more because satellites, the older satellites are become unoperational, and ISRO would have launched few new satellites, and those costs definitely would have been more than what specified here. But this is only a number which specified the beginning of the operational year. Okay, there is a question: why India need a NAVIC? Why can't already every system in India uses GPS as a in their mobiles and day-to-day activities? Why India spent this much money and this much technology, invested many scientists and other stuff time in developing this NAVIC and making it operational? I remember everyone knows about the 1999 war between India and Pakistan. During that time, Pakistan occupied many of the Kargil region, and they were upper hand. During that time, all our equipment which are operating using GPS, all are not worked because the US government take a decision to switch off the GPS data or GPS signal around that region where Kargil and Leh Ladakh, Jammu and Kashmir area. So all GPS enabled equipment were unusable, and India cannot do anything with them. So India fought a traditional war, and you know the result, we won it. But we had lot of property and human loss during that time. So that's when India decided, I think we should have our own NAVIC system or in regional navigation satellite system, which help us during these critical scenarios where India could have done much better than what was happened during 1999. Okay, it's this slide gives how this GNSS work. There are, as we discussed, there are 24 satellites in the GPS, 8 satellites or 7 operational satellites in IRNSS, in the satellite segment, in the space segment, and they will be keep on sending the navigation message, satellite ephemeris, all these information in the L1 or in the L5 and the S1 in the case of IRNSS, L1 in the case of GPS. So the users like the end users like aviation, marine, the navigation equipment on ground will use this signal and try to measure their position, and with that they enable their navigational accomplishments as they planned. And you will have this entire system will have master control, which will be in a control segment, and it has 24/7 real-time monitoring how these satellites work, how the satellite health and other stuff. And also there will be a data uploading stations where some of the necessary data needs to be uploaded to the satellites. It will be sent. That's about this. Yeah, this is our point of interest in this session. How typically the user computes its position using the satellite segments. Typically, to have a 3D, means three-dimensional position, we need 4 satellites. we know the XYZ means we will be talking in the Earth-centered, Earth-fixed coordination system, ECEF. In that, XYZ represents each axis, X, Y, Z axis direction, and the fourth dimension is the time. Each satellite will have an accurate quantum clock, which is very accurate and provide precision timing information at what time the signal is transmitted to the Earth. So those information. So each satellites will provide the user X, Y, Z and time, and user using these X, Y, Z and time from 4 satellites, he can accurately identify his location X, Y, Z on any part of the Earth. Since if we are talking about GPS on any part of the globe, but if we talk about NAVIC and IRNSS, any part of the coverage area what we specified earlier slide. So we know the distance equation. In the similar fashion, the range between user and the satellite is calculated by the equation which I showed at the right bottom of the slide. So XYZ is the one which we don't know, and the time, the delta time is there is a time lapse between the signal reception from the satellite. Each satellite are in a different position, and each satellite will have a different time of this, or the user would have received the signal in each different time time sampling rate, all those stuff different. So that will be calculated as a delta T. Let me put this up. Yeah, delta T. Yeah. So with these 4 equations, we know x1, y1, z1, x2, y2, z2, x3, y3 because of the satellites, and based on this equations, 4 unknowns, we need 3 accurate data x, y, z in the ECEF coordination system, and that will give us the accurate XYZ position of a user on Earth. Here we have I have provided some of the concepts how this position theoretically how this position is computed. Still there will be a element of error. We will discuss in further slides why we need this position position calculation is important. Various applications you would have come across in previous sessions. Basically, there are humorous applications where GNSS is used, surveying and mapping, precision agriculture side, intelligent vehicles, navigation, air navigation, they use in oil exploration, fishing and boarding, whatnot. They have ample now in the new era. We are using this urban air mobility, or drones are critically famous, and that are used mainly used on the navigation satellite system. Operate on the satellite navigation system. So there are many users. Okay. What is the okay? We know IRNSS is there, the GNSS, GPS is there. What is stopping it? What are all the limitations? Why we are not able to get, or why we are seeing an error in the GNSS standalone GNSS calculation, and what factors are impacting the position error, and what is the amount of the error? So how we can mitigate it? So all these things I am just giving you a pictorial view. definitely a 36 kilometer. If you take about IRNSS or NAVIC, satellites are positioned at 36,000 kilometer above the Earth, and the signal travels from ionosphere, troposphere, and it needs to reach the user. As you see in the picture center of the slide, but in those there will be lot of ionosphere, lot of delays in reaching the signal due to ionospheric refraction, tropospheric reflections, or delays, and there will be signal masking if any buildings or trees come into picture or clouds come into picture. There will be masking, and there will be multipath where the signal can reach the building and then the reflection reaches to the user. It will have impact of range, increasing the range, and that will disturb the position computation formula which we discussed in previous slide. And also the in this IRNSS or GPS, if you take the geometrical dilution of position, which see there in GPS case, if you see 24 satellites are sending, at least the as per my knowledge, the receiver are capable to receive the signal from 12 satellites. 12 satellites position may be in a different places. So for position computation, typically they use 4 best satellite available 4 best satellite signals, and based on that they compute. Suppose if you see in the center of the slide, bottom center, there is a position uncertainty where if you receive a signal closed from satellites which are positioned close, you may get good satellite geometry, or if you see you may not get the good satellite details, which eventually give us the bad or more error in the position computation. It's all depends on the geometry where we can where the satellites position at the time of signal reception at the user level. So which is generally termed as GDOP, geometrical dilution of position. So all these factors, whatever mentioned in this slide, will impact the range calculation between satellite to the user, which in turn affect the position accuracy. If you see the right bottom, there is a table which is specified by ISRO when they came up with this NAVIC. Typically, based on them, the error, all these error contributions will typically range to 20 meters error. So, if we use the standalone NAVIC receiver, the expected accuracy is 20 meters. That is as per the specification. So, what is the solution then? Are there any? There are many solutions, but differential technique is one of the solution where which is low cost and it can be implementable by any institution. Jain University we have done, so universities can do, some of the organization can do with less cost involved. There are in this differential calculation, basically there will be 2 IRNSS stations. One is reference station, another one is the mobile station. The reference station is positioned on the accurate measured place where they know the XYZ latitude, longitude, and altitude details of the position, and with that they can calculate the error, and that error can be applied to the nearby flying or nearby mobile user, which in turn correct their position accuracies and position errors and improve the accuracies. So this is the high level concept of differential. Basically, we need two receivers, one on the mobile station, one on the reference station. And there will be a data link, or there are several methods that also we tested as part of my research. We can send the errors. How we will send the errors? That depends on the user, the application what we have. So based on that, we can use. There is a data link available. Some people is good. Some applications are good in the post processing way. They can correct the positions and they compute their required position accuracies. Or some of them can use directly through internet, through IoT way, and send these errors to the user. So whatever way data link, the concept is find out the error at reference station, send it to the mobile station, and correct the position error in the mobile station and improve the position accuracy. I think that is the concept. In differential techniques, we have three different topics. One is differential position, differential pseudo range, differential carrier phase. Differential position is a straightforward, simple method. You have latitude, longitude of the user, and you have corrected measurably accurate latitude, longitude of reference station. Subtract them or add them and get the error, and that error apply there. That is a simple method, but not impactful. If you see in the table, it's a simple, but definitely it has a lot of errors inbuilt. It doesn't calculate many computations, or it doesn't calculate many error factors what we discussed in previous slide. The better one would be the differential pseudo range, where it impacts the range equations of each satellite and try to eliminate many error factors like the time delay, offset, clock offset, and the masking, and many other error, instrument errors. All those stuff it will eliminate, and definitely better than the differential position technique. There is the third one, differential carrier phase, which is better than the other two, differential pseudo range and differential position, but we haven't. At least I did not do. That will be a future scope of research in this topic. If someone interested, they can work on this and try to come up how we can how this technique improves NAVIC position accuracy. I think that is the future research opportunity. Let me go to the next station. So as I explained in the previous slide, there will be two stations in differential technique. One is base station or reference station, where we know the position, latitude, longitude, or XYZs in terms of ECEF coordinate system. We know accurately, and we are trying to calculate the error, and based on the error, those errors will be passed, send it to the mobile station. Mobile station will correct their range equations according to this satellite error provided by the reference station and improve their position accuracy. So that is the topic. In my research, the method what I used, we know the latitude, longitude, convert them into ECEF, and for ECEF coordinate system, compute GDOP of out of this 7 satellites, compute the GDOP and determine which 4 best satellites, means geometrically best satellites. Take that information, compute differential error for each satellite, and that error transmit to the mobile station. Mobile station uses this differential correction for their range calculation, and then correct their error, improve their position. So that is the methodology what I used in my research. Yeah, the same thing I have mentioned in the flow chart. We have the reference station, latitude, longitude, convert them into ECF, calculate the range equation for the 4 satellites, and then compute pseudo range error, and then apply them to the differential pseudo range correction to the mobile station, compute geometric ranges for each satellite from mobile station, and then subtract or add based on the using this equation. Then you have the 4 best satellites, and you have the differential equations. This I will show you in one another slide where what I refer to get this navigation solution. So using this differential directional derivatives, compute the x, y, delta x, delta y, delta z, that is the errors, and those errors are used in the mobile station to correct its position. So that's the overall. Let me go to the other solution. 1 second. Yeah. So my pseudo range equation, my calculations are based on the Peter H. Dana. He has come up with the solution, this navigation solution in 1996, where he did it for the GPS pseudo range, differential pseudo range, and the same formula which I used in my computation, I applied this technique to a Navic system and try to get the errors in each XYZ direction, and these errors are applied to the mobile station. So 4 satellites, we have XYZs, and satellite pseudo ranges are available in our the data what we received from. I will show you the Excel data so that it will give you some more some clarity for everyone. And we know the receiver's position XYZ converted into range equation, and for each of 4 satellites, compute ranges are, and then try to come up with the predicted ranges, receiver predicted ranges, and from that you compute the directional derivatives. We will have the formula with all these 4 satellite data dx derivatives, and using this dr is the metric where you can get the delta x, delta y, delta z, and delta t, which is the errors, and those errors are applied to the mobile station's ranges, and that will give us the accurate position of the mobile. So this is I referred this, and you can always go to internet and we can study Peter H. Dana's. He has his own website where he explained many concepts about the GPS, and I really had difficulty during my research to get the right equation, pseudo range equation, where I can get the errors. I referred many papers, but I found this is the best one, and which I easily implemented in my pseudo range calculations. what I did, I have all these things. The data is available, and Excel, using Excel, I can compute, I get the directional derivatives. And for this particular finding out DR matrix, I used Python code. I created my own Python code, and that code helped me to get this derivative. And then I calculated the corrected receiver's position XYZ. Hope I gave you the right information. I will go back to, before I get back to my presentation, let me give you some details about the stuff. Give me a minute. What generally we get the details. In general, the receiver what I used in the GPS or for this experiment will get you this. Yeah, these are all the typical data is available with to you to process, to study, to analyze and get this one. So we will have and that receiver which I used is capable of receiving GPS as well as IRNSS. L1 is for GPS, L5 and S1 is for IRNSS, and it has position details which is for the position. This has the position details of the receiver, and satellite details L1, L5, S1, carrier frequencies of GPS and IRNSS. These are all the typical data. I may not go through all the details, but I will go through the satellite data where our pseudo range equations are typically used. So let me go to this. Yeah. So based on the satellite data of the whatever we received from the receiver, TOWC, I know everyone aware of this. This is time of week count. It is keep. That is the reference for each data with this one to compute which time, what data, what position, what error is transmitted and other stuff. So we have XYZ position of the receiver, and PRN reference pseudo range number is given to each satellite. PR is, so in this calculation I used the 4 satellites, 2, 3, 6 and 9, which are the best as per GDOP. I took this data and took the main topics, like we know we want this as per this equation. We need pseudo range. So we need pseudo range. So yeah, we need the satellite XYZ we have, and we have user position XYZ we have. Pseudo ranges is given here for each satellite. For PR2, satellite number 2, we have range, and we have delay, tropo delay, satellite XYZ position, satellite clock correction. So using these data, calculated the error, PR satellite error, pseudo range error, the same equation what I have mentioned earlier. And then for this is PRN3 calculated for the satellite 3 and respectively for satellite 6 and satellite 9. And based on the same formula, I have calculated directional derivatives of XYZs for each satellite. And I have this with me, all these details for all satellites. Then using the code which I developed using Python. I'm just showing you the code with using this code, Python code. I came up with the derivatives, and let me show you that. Yeah. So using that code, I have for each time of reference time of code, I have dx, dy, dz, and dt. Dt is a time difference or delta t. So I have for each satellite TOWC, each second, what is the satellite position is given, and what is my dx error for each satellite for each TOWC. This is applied to the mobile range equation for the same TOWC so that I can get the accurate application of the error. So I can show you how I used in another. Okay, here. Yeah, how I use it this to compute. Yeah. So I have now the RX, RY, RG. This is mobile station on that particular time of this one. I have DX, DY, DZ, DT of the errors, and I got the IJK columns shows the corrected position information, and I know the reference station XYZs. Find out the between for this application. I need to find out the distance between reference station to user. So with the corrected positions, I know what is the error. So the error is with measured distance and computed distance. The error is, you can see the range. I can show you in a different slide how the error looks like. So it typically ranges between less than a meter to 6 meters. That's the error measurement using the differential technique, pseudo range technique, what I used to improve the position or reduce the position errors and improve the accuracy. Okay. So these are all few stuff. Let me go back to my presentation. Yeah. So all my equations and all my the error Excel sheet data computation, the code, Python code is talking about these three pseudo range flow charts which I mentioned in these two slides. This is the overall process. First, calculate the error at the reference station, apply the error in the mobile station, get these derivatives according to that navigation solution, and get the accurate error corrections on the mobile station. So that's the three-step process how I calculated them. And as I mentioned earlier, the data link, how you will transmit the error between reference station to mobile station. Either you use the SBOS, SBOS system, where we use a dedicated satellite to transmit receive the error from the reference station, transmit the error to mobile station. That is the SBOS system. There is a GBAS system as well. In the GBAS system, there will be a dedicated real-time data link VHF or using VHF station. There will be a dedicated system where the data is transmitted at real time. The real-time position accuracies are computed at a mobile station, and the application what we intended to is made successful. And there are several other applications where post-processing method is applicable, where they can able to have those information post-processing. So those applications are done. And some of the applications we have tested using the IoT, using the internet. Instead of VHF data link real-time system, we used the internet as the medium of transmitting the data from reference station to mobile station. So there are many. There will be some more types where the experiments, the data link, the medium of transmitting the errors between mobile and reference station and mobile can be achieved. But in my experiment, I used these three. Okay, now we I don't know how to avoid this. Anyway, fine. So I have the these are all the systems what I used in my experiment. The IRNSS receiver, which is provided by Accord system, in turn supplied by ISRO to that university, is provided here, and we have a laptop to receive the data or log the data. The similar system is employed in the mobile station. This, if you see here, this is my car where I put the same system in my car, and the mobile station is powered by the battery. You can see here. So mobile station is powered by the battery, and the antenna is positioned. This is the reference station where the antenna is mounted on the top of the terrace. The mobile station, the reference station also, we have we got accurate positions from Survey of India, where we identified the accurate positions where we put our antennas and measured the accurate position for the reference station. And the mobile station, we used tempo travelers. Sometimes we used buses. Sometimes we used my own car as a mobile station, and we conducted the tests. And the same thing what I showed you earlier in Excel sheet, how we what data we used and how we computed the error, pseudo range error. So that's about this. And as I mentioned, we got 5 accurate locations from Survey of India, which is we predominantly took Jain University as a reference station, and we predominantly were looking into the nearby ranges. So we have identified these 5 positions: Kungal, Halguru, Mandya, Magadi, and Devanhalli, where we got the Survey of India provided us the accurate positions. Unfortunately, Mandya and Devanhalli, the stone what they generally lay out, which are missing, so both of them were unusable for experiments. But we used Halguru, Kungal, and Magadi for our experiments, having them as a reference station, and we conducted our tests. Yeah, I think Dr. Raju sir also would have showed you and discussed on various experiments, whatever we have done. The same thing, I may not take much time, but these are all the main thing. Jain University, these are all various tests what we conducted, where we used Jain University as a reference station, and then we have done few experiments. And few experiments we have done. You might see a iron stamped on the wooden cemented block, which is the one which is we got it from a Survey of India, and where we positioned the antenna, and then this is you can see the right picture, like top, where the yellow represents the reference station, and green to red is the mobile station movement. So this is one of the typical exercise where we measured the distance between green and red, and we based on our pseudo range corrected position, what is the error, and then that we compared with measured error, and we know what is the pseudo range algorithm what I used in my research is improved, how much it improved. So that's the thing. And this is on the Kungal station, and the one which you see at the right bottom is the Halguru station ROI. Yeah, and the other one is in the Magadi. fortunately, the Magadi GCE, this survey of India position is inside of the playground, and it is in one corner. The orange icon in the chart is the reference station, and all the green ones are the various mobile stations. This we used it for another experiment where A90, B90, B60, B120, C90 is different directions. 60, 90, 120 indicates the distance between the reference station to that position. So we measured this distance and we get the position accuracies, and based on that calculate the distance. We compared both of them. So how our position in pseudo range, differential pseudo range is able to measure compared to the measured one. So this is one of the experiment. And if you see the left top, this is the typical. We have the laptop, which is nothing but a data logger, which has the all the data will be logged. All our software will be a part of this laptop, and the receiver, Navic receiver, which is powered by the battery, and there will be a cable to antenna, and there will be a cable to laptop, and cable from power source to the receiver. And here we can see left bottom the antenna positioned on the GCP position what we received from Survey of India from at the Magadi school background. Sorry, ground. Okay. And this slide gives the data link exercise what we did. Okay, the data link exercise what we did using the internet. Post processing method we used, and using the internet. I think the SIM7600EI, which can be mounted in both laptops, user station and mobile station, which is capable of receiving the error between reference station and transmits through the internet and gets transmit to the mobile station. So which is the technology measures to the MQTT client, MQTT this one protocol. Sorry, MQTT is a protocol. So MQTT protocol, and this was successful, and we did the measurements. And I have a paper on this. You can refer to that paper, and you can get to know more details about this transmission. These are all the various observations. Typically, the error range what we see is plus or minus. These are all satellite pseudo range equations. If you see at the left side, plus or minus what you can say 4 meters. Sorry, plus or minus 4 meters. And the center distance to GCP, I know I showed you, we did having the mobile stations 90 meters, 120 meters, 60 meters from the GCP point, and how it ranges. So before corrections versus after corrections, if you notice the errors with differential PR corrections, with my logic, the error what we saw is less than a meter to 6.4 meters. Errors computed without the logic which I developed is between 7 meters to 25 meters, as per the defined specified by the ISRO. But with my differential pseudo range algorithm or a code what I developed, which reduces the same in terms of 0 to 6 meters. And the same you can see in the graph at the right bottom. Yeah. And in another exercise, I used comparison between GPS and Navic. If you see, in the GPS, we have used for, there are many satellites available, maybe. Uh, Various satellite combinations, 15 satellite combinations we measured. The same thing we used in the Navic also. You can see the distance error measured using these satellite combinations. In the GPS, we can see three satellite combinations are very, very bad. And very few, one or I think three satellite combinations gave us the measurements lesser than a meter. But if you notice in the IRNSS or NAVIC at the same time, there are eight, 1, 2, 3, 4, 5, 6, 7, 8 satellite combinations are gave us the distance error lesser than a meter. Which used by the algorithm which I developed, and the two configurations are very bad, but that too it's lesser than 40 or 50 meters if you look at it. But if you compare to the GPS table, distance error computation table, the errors are too bad. 382, 343. The bad is more worse. So this is one comparison, and one of my paper I presented in this. And if you come to the right hand side two graphs, we have done experiments on different weather conditions to check how the values are computed in different weather conditions. So sunny day and rainy day, we have done the experiments. The red line indicates without applying any errors. The blue line indicates the Accord receiver system has inbuilt position correction system. With that, how much? And the green one is the one which the measurements by the equations developed by me. So if we notice, the green one is better than all the blue and red. And if you see the rainy day, the measurements are I think the sunny day measurements are better compared to rainy day measurements. That indicates the rain has the precipitation, and that causes more range errors. That could be a reason. So this experiment provides all those details. And yeah, these are all the support system what I received from Jain University. Jain University provided me the mobile station, tempo traveler, receivers, all the equipment which are all necessary for conducting my experiments. And we used solar systems, solar panel, solar UPS to conduct, means we do not want, in one of the experiments, if we do not have a traditional electricity board supply, then what kind of alternative sustainable energy sources? So we use solar as a power source to both mobile and reference station, and we have conducted the experiments as well, which is really a good experiment, which the ISRO also appreciated for us. And if you see the right bottom, this is the solar UPS which we used to power both reference station and mobile station during our experiments. Okay, it is not end of my session. I think now 8:23. I have Mukesh. How much more time I have?
Sir, another 5 minutes, sir.
Oh, okay. I have accurately came to the or accurately used my time what is given to me. Okay. The motivation for taking up this subject as part of my research is while I was working in Hindustan Aeronautics Limited, I was part of advanced light helicopter development, and as part of that, I need to test few measurements, landing and takeoff measurements to satisfy DGCA or SEMILAC for military applications, regulatory requirements. So we used differential global positioning systems as a flight test equipment to measure those, to conduct those flight tests. And I was major part of that, and I was one of the main contributor to develop a software, user segment software, which accurately accurately provide the location details of the helicopter. Helicopter is a mobile station in this case. So that was I was at the user end, and I was really fascinated about this topic, and that's more encouraged me to take up this subject when Dr. Raju sir offered me for my PhD, and in this I could able to do it in a as a researcher, part of the NAVIC development program. I came up with the differential pseudo range algorithm, where I showed the improvements. Position accuracy error can be reduced, and accuracy can be improved lesser than a meter, and that was and it's well appreciated by the all research fraternity, and that gave me resulted into my PhD. Okay, this is what I was talking about. I got an opportunity to develop a software which are used the flight test engineers and flight test pilots, and based on that they used to plan the flight test for the ALH. So that was wonderful opportunity, and eventually I got into the PhD research. And yeah, this is my research objectives. I don't need to spend much time. So these are all my papers already published in SAE. The first two papers are published, first and fourth paper published in SAE, and the real-time data link, there is a paper, and method of assessment, two static, one of the experiments, both are presented in the Grinch GI JET. So yeah, this is my PhD certificate, and Dr. Raju sir is my supervisor, and definitely I need to thank Dr. Raju sir for giving me a good opportunity to work on this particular research, and definitely there is a lot of scope for future research on this particular area. So differential carrier phase is yet to explore, and definitely welcome to give my support to everyone if anybody wants to pursue the PhD in that. And also I would like to thank Dr. Mukesh for giving me this opportunity to present the research and talk about the topic what was asked me to for this session. Thank you very much, and thank you very much for the all faculty members who is attending and understanding about this topic. Yeah, that is Mukesh.
Thank you, sir. Thank you for your wonderful presentation. And having one doubt, sir. Instead of
Yeah.
Survey of India locations, can we use Gagan as a reference receiver? From that, we can find out the errors that we can transmit through internet or by using some other medium to the rover station.
Gagan. Yeah, Gagan is operated using global positioning system data. So there will be, see, many errors can be corrected, but multipath is definitely uncorrectable using this. And definitely that element of error will be there in the Gagan position also. So we may need to go with that error. Why we used Survey of India is they have a different set of methods. They accurately 6 decimal points they will give, and that's where we can rightly measure or rightly compute and evaluate the algorithm what we developed.
But what is the main problem associated with the Survey of India? It is not that much easy to get the survey measured location.
Yes, I understand. They actually write an MOU between university and Survey of India, and they charge for number of that time when we wrote MOU between Survey of India and Jain University, it was 5,000 rupees per the GCP point. So we took 5. They give some concession, some discount, and they charge only 20,000 rupees. So yeah, it is difficult to get, and we almost waited for 6 months to get this. But another method, I think Dr. Raju sir would have explained, 72 hours of standalone receiver logging. See, one what you said, Gagan, we can use. There will be a minor error. And also the 72 hours or more of standalone logging, taking the RMS average of that position data, and we did few measurements, using experiments using that. Even that has better error reduction and good accuracy improvement. Mukesh, I think we can alternatively use that.
That is 72 hours of what the thing is in open sky location, or we have to stand in near to some of the terrestrial place like that.
No need to. What we did is 5th floor of the that Jain University building, we mounted the antenna, and we we ensured there are no multipath or masking and other stuff. So we computed that, and with that position as a reference station, we did the experiment.
Thank you, sir. And also here, what the thing is, we have seen on Survey of India location. There we went and measured the location, but what the thing is, that was measured long back. So it is absolutely what the thing is, having lot of error with respect to GPS or Gagan measurements. So every time we have to have a new measurement, sir.
No. That's what. If we go with Gagan, every time you will have different position information will get. But if we go with Survey of India, at least for next 5 years, I think every 5 years they do. That's what I understand. The position will not be changed. It will be same.
But we don't know when it was measured. That was
no, they will when they give us, right, they will give the survey's date also. Based on that date, their data is measured.
Okay, sir. Okay, thank you, sir. Participants, any doubts? Please ask. I think no doubt, sir. So now I request Dr. S. Kritika to deliver the vote of thanks.
Yeah, very good evening to one and all present here. It's my privilege to deliver the vote of thanks for today's enlightening session. First and foremost, I extend my heartfelt gratitude to our esteemed chief guest, Dr. Ramesh Raju, for sharing his deep expertise on positional accuracy enhancement and differential navig. Sir, your insightful explanations on advanced navigation techniques, error sources, correction methodologies, and real-world aerospace applications have truly enriched our understanding of modern positioning systems. Your ability to bridge complex technical concepts with practical industry experiences has made this session highly valuable for researchers and professionals. We are deeply grateful for the time you have taken to guide us and for the clarity and inspiration your talk has provided. Your presence has made this event truly special, and we look forward to learning from you again in the future. I also wish to thank our management, Secretary Sir, Principal Sir, Head R&D, HOD Ma'am, faculty members, organizing committee, and all participants for contributing to the success of today's session. Once again, thank you, Dr. Ramesh Raju, sir, and thank you all. Have a great day.
Thank you, Mukesh and all.
Thank you, sir.
Thank you, sir. And I request all the participants to fill the feedback for the both the sessions. And also tomorrow, kindly join by 2 p.m. because tomorrow 3 sessions are there. Please join by 2 p.m. And tomorrow, once all the 3 sessions are over, we are having the test at the end of the session. Thank you. Thank you, one and all.